Okay, so do you know what dark matter is?
Only because you just told us.
Okay, so yeah.
Nobody really knows what it is.
We don't know what it is. It's a mass that's out there in the universe. We measure it in galaxies mainly. When we measure how fast galaxies rotate, we find that they're rotating a lot faster than they should be if all the mass they contain was just in the visible light. So when we add up all the stars that we can see, the mass that we measure, it doesn't add up to how fast they're spinning. If you use sort of Newtonian dynamics, standard physics, there's a lot more mass in there than we can see. So we think there's this.
It back to when everything started moving to find out how fast they should be moving today. That's what
No, it's actually a very simple equation. It just relates the mass and the radius of the galaxy to its rotation speed. And you find that it should be slowing down at large radiuses, you know, big spiral galaxies where they have spiral arms and they're spinning around. You find that as you move outwards, there's less. So if you know what a galaxy looks like, there's a big bulge in the center that's very bright. And you think that most of the mass is in the center. As you move outwards, this kind of theory of gravity says that it should start to slow down because the density of mass within it is decreasing because there's less stars. But what it doesn't, it stays constant. So the outside of the galaxy is spinning just as fast as the center. And this kind of suggests that there is something within that galaxy that's dark, that's not giving out light. It's not stars, it's not gas, it's just completely dark. And we don't really know what it is, but we know it's there. And we can measure it with other ways. So it's been measured from the cosmic microwave background, which is this sort of relic radiation that comes from so after the Big Bang, about 270,000 years after the Big Bang, there was a moment where the universe basically became transparent to light, to photons. And we can still measure those photons today. If you know, back in the olden days when you had to tune your own TVs, if you go between channels, you would have seen static. And within that static is actually some of the cosmic microwave background. So when this was actually discovered, they thought they had, the guys who discovered it with radio telescopes thought that there was some bird poo on their telescope because they were measuring this constant radiation from all over the sky, and they were like, what is this? This must be...
It used to be referred to as the cosmic hiss. Is that
Yes, I think, yes, it will be, yeah. So it is just like a hiss in radio waves. It's this noise, and it comes from all over the sky. And what it actually is it's photons, it's light that was emitted back, you know, very close to the Big Bang, about 270,000 years after the Big Bang. And we can actually measure these photons, and they tell us, you can measure them across the sky, and you can look at the temperature differences between points in the sky, and it gives you a picture of what the universe looked like, you know, very early on. And you can see that most of it was, compared to today, where you have a lot of structure, so you have galaxy what we see in the universe now is filaments and voids. So we see big empty spaces, and then we see bits where there's lots of galaxies. But back in the early days, it was a lot more uniform, but there were sort of patches that were colder than others, so the temperature was very varied across the universe in the early days. But what we can actually do is measure that, and it tells you something about how much matter there was at each point in the universe. And you can see that what we can tell from it by some very clever theory, which I don't understand as an experimentalist, we can tell how much dark matter there was in the early days of the universe at different points, and we can see that what it did was it seeded galaxy formation. So dark matter interacts gravitationally, it's heavy, it pulls things onto it, and the dark matter back in the early universe started to pull normal matter like the gas and stars and dust onto it, and that's how galaxies form. So dark matter is actually essential to our own existence, because without it everything would have just stayed very uniform. There wouldn't have been stars and galaxies. So it's really important stuff. So we can measure it by that as well, and we can also measure it by how much, so we can measure the mass of galaxies and galaxy clusters by how much light they bend around them from a distant source. So this is called gravitational lensing, and this is where you observe like a very, very bright distant source, and you can measure something between us and that source. If there's something there, the light is actually bent around it. So you can actually observe what's called an Einstein ring, and you can see that image of that distant galaxy is repeated across the sky in a ring because of the light being bent around it. So we can also measure, that's another way we can measure how much mass there is somewhere. And again, we keep finding consistently that about 90% of the mass is not visible to us. So we understand pretty well like the sun and stars and how much they should weigh. But when we add up how much light there is, it doesn't match up with how much we measure from this sort of gravitational lensing. So that's why we know that there's this stuff there that doesn't give out any light, which we call dark matter. So your question was originally about it going underground. So we know it's there gravitationally, but we try and detect it by another way because we think it's a particle, because everything around us is made out of particles. So we're made out of atoms, and protons, neutrons, electrons. We think that dark matter is also a particle, but just one that doesn't give out light like our atoms do. So we basically look for it interacting via something called the weak force. So there are 4 forces in nature, which are gravity, the strong force, the weak force, and the electromagnetism. So electromagnetism is the one we're most familiar with because it's how we see. We see by light. Light is a photon, it's an electromagnetic particle. Everything around us interacts by the electromagnetic force, but dark matter, we know it doesn't because we don't see it. The gravity, obviously, we're on the Earth, we're not flying off, so we understand gravity as well. But with the dark matter, we think it interacts also by this weak force. So the actual particle of dark matter we look for is called a WIMP, which is a silly name, stands for the weakly interacting massive particle. And this is actually our best theory for dark matter today. So there are some really nice sort of theoretical motivations for thinking that dark matter interacts weakly, which is basically how much there is, when we measure how much there is by its mass. If it was, in the early universe, if it was kind of interacting by this weak force, it basically all adds up to give the right sort of amount that we measure today. So we really have very strong theoretical motivations for it being weakly interacting. But so what these detectors do that I work on is we actually look for the weak interaction of a WIMP with an atomic nucleus. So what we're actually looking for is a very specific interaction where the WIMP comes along, it knocks into an atomic nucleus and causes what we call a recoil, nuclear recoil. And so this is why I have this bucket. So this is kind of the basic analogy of the detector we use. It is just a bucket it's not made out of plastic, it's made out of titanium, but it's a big container of liquid xenon. And xenon's like a very heavy nucleus that has quite a high probability of interacting with the dark matter. And
lots of bits for it to hit into.
There's lots of
stuff in the
yes,
xenon.
it's very dense, exactly. So it's a very dense liquid, and it contains these big heavy xenon nuclei. And so the problem is with that though is like every other particle out there will interact with the xenon as well. So that's why we have to go underground. So that's what I was getting to. Is we take this bucket, and the other important thing about xenon is it gives out light. So you may know car headlamps are sometimes made from xenon. So xenon is what's called a scintillator, which means it gives out light when particles pass through it. So that's kind of the idea. You get this bucket, you wait for particles to go through it, they give out light, and you detect the light with what are called photomultiplier tubes, which are these light detectors. And we put them on the top and the bottom, and we view the bucket, that's why it's clear. Xenon is very, very clear to its own light. So when it gives out the light, it just passes straight out, we can detect that light. But every other particle will do the same thing. So photons, electrons, neutrons, anything that comes through the bucket will also give out light. So that's the main reason we go underground, is because so on the surface of the Earth right now, we're getting bombarded by cosmic rays from space. So these are particles, they're just high energy particles, they come down from space. Sometimes they interact in the atmosphere, they create other particles, and we're getting bombarded with them right now, but we just don't, they're not dangerous. You've been bombarded by them your whole life, but you wouldn't know. But our detector is so sensitive that it will see them. So we have to put it, so it's actually in what was a gold mine in South Dakota in America. It's 4,850 feet, about 1.5 miles or something, just over a mile underground. So they ran out of gold, so they allowed us to turn it into a science lab. So it's now a dedicated science facility underground, and we put the detector down there because then it means that the rock absorbs all this radiation from space. So it's very quiet down there, like as in quiet in terms of the amount of particles around you. So that makes it much easier to try and detect dark matter down there because it's so much quieter. So I had, thank you. So this was my analogy, was that, so this is a cat. You see a lot of cats on Earth. These give out light in the detector just the same way that dark matter does. Now dark matter is is a unicorn, so we don't know that unicorns don't exist because we've never seen one, right? So it's the same thing, thank you. Same thing with dark matter. We don't know they definitely don't exist, but they will also just give out some light in the same way in the bucket. So we have to, this is the thing is that up here there are lots of cats, so we go underground. We also try and shield the detector in lots of other ways. We put it inside a big tank of water to try and absorb some of the, so that's the thing with rock underground, it's radioactive, which means it gives out particles as well. So the whole motivation for these underground dark matter searches is yeah, we want to avoid the cosmic rays, but then we go underground and the rock is spitting particles at us as well. So that makes it's equally difficult. So we put it inside a big water tank, and then what we actually finally do as the final layer is we take the bucket and we basically just look for dark matter right in the center, because everyday particles, they come in and they immediately interact with the xenon.
How big is your bucket?
Okay, so it's a bit bigger than this. So the early the early dark matter experiments were even smaller than this. They were very, very little. And there was one up in Bulby Lab in Whitby in the UK that was kind of probably only about that size, very, very small. But it was like a proof of principle, and it worked. And they were like, okay, we can scale this up, because this technology is very easy to scale. So the one we have now is probably about this tall, like from me, nearly as tall as me, about this wide, and it contains about 350 kilograms of liquid xenon.
You look in the middle of the dark matter.
And we look right in the center, like just kind of a sort of circle, cylindrical section in the middle. And we say, and it's very quiet in there. Supposedly it's the most radioactively quiet place in the world, apparently, is the center of this detector. And right in there, there's nothing interacting, because all the standard particles, the everyday particles, started to interact around the edges. So we look in the middle, and then we just have to wait. That's the idea. And we've ran for a total of about 400 days now, and no dark matter has turned up, unfortunately. But that's not the end, because the thing is you have to, what you can do when you don't find dark matter is you can rule out certain sort of types of dark matter, and you can say, okay, so we know we haven't seen it, so that means that dark matter of these masses and these sort of probabilities of interacting with the xenon, they're not there. It's not. We know that dark matter is not here because we've looked here and it hasn't shown up. And the kind of analogy with the unicorns was like, there's some portions of the magical forest where the unicorns don't live, but they might live somewhere else. We have to keep looking, and we can keep looking by making our detectors bigger. So the bigger the detector is, the more likely it is that you might catch.
You'd look with bigger detectors in the same place.
So we haven't done yet, but that's what's happening. So the detector I work for is called LUX, which is the Large Underground Xenon Detector, and LUX has just finished its second sort of WIMP search run, as we call it, where it's finished taking data now, and we haven't found dark matter, but we have managed to put the world's sort of best constraints on the dark matter properties. But that's not the end, because we still haven't found it. So what's happening now is we're taking LUX out later this year. So we take it out of the water tank that it's in underground in South Dakota, and we're going to put in a bigger version, basically. So this one is about 350 kilograms of xenon. The next one is going to be 10 tons. So it's a big scale up. And that's what's really great about this technology, is you can just make it bigger and it becomes more sensitive. So the bigger it is, the more likely you are to have seen a dark matter interaction. And so we've also got a load of other features coming in, like we have what's called an external veto, which is like a detector around the edge that will detect any particles coming in, like neutrons, for example, that will give the same signal as the dark matter within the detector. But we can veto them because we've seen them coming in. And dark matter interacts so rarely that it would be a miracle to see it one time, let alone if we saw it.
So has it ever interacted?
Well, we've never seen it. So, I mean, the thing is about it, this search, is that we are making some assumptions. Kind of says that dark matter will interact via the weak force with xenon in this way. And it's very well motivated in terms of the theory, but in reality, like, physics does not always align with what we think it will, it doesn't always work. So we're kind of, it's a very similar search to the Higgs boson. So everyone's heard of the Higgs boson. The theorists came up with it 30, 40 years ago, and they only just detected it now. So it's kind of a very similar thing. We've got the theorists have come up with these sort of particles, and we think that this is what they'll do. So we have to just try and detect them in the same sort of way.
Are you sure that the layers of rock above you and around you are not masking? What if they're getting all the hits and it's not getting to you?
Well, that's a good point. But the rock, so the idea is that right now dark matter is coming through as about, I was saying, like 1 particle per pint or something like that. The sort of material the rock is made of is lighter, actually. Xenon's very heavy, and the interaction probability of the dark matter with any sort of atom, it scales with the size of the atom. So it scales with the atomic number squared, which is like the weight of the atom squared. So the heavier the thing is, the more likely it is to interact. So it's a very good point. There's no reason it can't be interacting in the rock on the way down.
But you know that rock is generally lighter than the xenon, so
yes, it's less likely. And it just helps us immensely by cutting out all the cosmic rays. So it cuts out all the background. We'd never have, if we had a detector up here, it would be lit up all the time.
I want to see that.
Want to see
we
the
want to see that.
well, the detector?
We want to see it let it up all the time.
It's not very interesting because it's in a big tank of water, so you just see the water tank. Unfortunately, like no, it's but no, it. You know, we might not see anything. We might build the bigger one. We still might not see anything. But the thing is we can rule things out, and that's kind of all we can do right now. Until we actually detect a particle, we only can rule things out and say, okay, we know it's not here. We should keep looking in these other places. So, I mean, it is important. Like someone asked before, what is the importance of this stuff? Like, why do we want to find it? And in terms of the gain for the human race, it's only in terms of expanding our knowledge and actually understanding the universe that we live in. And it would give us a handle on what might happen in the future. We might be able to understand the universe well enough to know in the future whether it will keep on expanding into nothing, whether it will collapse back in. There's a lot of, basically, the composition of the universe is like the biggest mystery of physics today because we don't understand 96% of it. We only understand the 4% that makes up us, the atoms and the electrons and the photons. We understand that, but that's only 4% of the entire universe. So the dark matter is only 27%, so there's a whole another big lump which is dark energy, which I don't know that much about other than it causes the expansion of the universe.